Okay, everybody drew this. It looks almost identical to what you have for mass and an incline. You've got mg going down, and you have the tension in the string here. So your free body diagram looks like what? Well, you might have a little confusion about which way to draw your coordinate system. But you're going to have mg here and t here. And you don't want to draw a coordinate system like this. At least not for a low amplitude pendulum, okay? Because for low amplitude pendulum, this angle is going to be pretty small, meaning this angle of tilt would be pretty small to start with. And the approximation that we make is that the thing's really just moving back in the x direction. And that's not quite accurate, and you have to understand why, because when we analyze that in differential equations, we get into the reasons why and how we model it if it isn't a small amplitude, if we take into account the amplitude. But for this course, we're not going to take into account the amplitude because, of course, we don't assume differential equations, which is a good thing because none of you have had it yet. You will soon. Okay, so, got it? There's the picture we use, and we use horizontal coordinate system. In this case, that's ty. We're going to have a y tension and an x tension, right? And then I'll make note okay. Now I'll go ahead and, origin's going to be here, and here is going to be position x. Okay? And you have length L. Okay? So for x much less than L, assume the magnitude of your tension force equals mg. Okay? Now, another connection, and we've done it, I'm not going to do it again, go find it. And your net force is going to be negative mg over x times, negative mg over L times x times the I vector. Does that make sense? Now the details of it are simple enough. If this is equal to mg, this triangle here is if ty is equal to mg, And I guess I gotta say, that we assume T equals Ty. It's a connection I was looking for and didn't have written down. Okay? Then this tension is mg. Okay? In other words, basically this tension is going to be equal to mg because this angle between here and here, the angle of the tension vector with the y-axis is small. So the cosine of that angle is small, it is close to 1, and remains close to 1 for, angles out to about 10 degrees or so, okay? Depending on how close you want close to be, okay? Depending on how refined you want to make your estimate. And as I said, if you go beyond the point where that makes a difference, you're into differential equations. We don't do it, okay? So we assume that the amplitude of this thing is small enough that this approximation makes no significant difference, okay? In that case, Tx is this leg of a triangle with hypotenuse T, and x is this leg of a triangle with hypotenuse L. Okay, meaning that Tx is mg over L times x. Okay? And that equals negative kx times your I vector. And once we have that, what do we know? What I asked you to review for the weekend and look up, and you probably didn't because you got a statics test or dynamics test Wednesday. Apply simple harmonic motion. Period omega equals square root of k over m, which equals square root of g over L. Now, you know what the equation of motion for this pendulum is. A cosine omega t plus phi, where A is your maximum distance from equilibrium. So this, you might as well write it down because it's really important and it's part of what you were supposed to review. Okay?